Okay. Does anyone have any questions before we get started on this week's material? Okay, why don't we get started? So this week is all about like applications. And so you can kind of divide these into applications in geometry, mechanics, and probability. So it's kind of like 3 sections of applications. The first one is our applications in geometry. So I'll just like quickly go over definitions and we'll do examples. But in terms of n-dimensional, meaning like if your domain was in 2D or 3D, no matter what, this n-dimensional thing lets us like generalize all our equations. But specifically, if you wanted to go into the n equals 2 case, so a 2-dimensional volume element, or specifically, if you're in 2D, it's area, right? So area, that would give you your area element, which is dA or dx dy. If you wanted to find we're in 2D, so area over some region, you do the double integral dA. Average value of any function, we do the same thing. So double integral of f over double integral of 1. Specifically, this double integral of 1, notice that it's the area. And then the centroid is a new thing. So you have like this x bar, y bar, where x bar is calculated in this way. So you have double integral of x area elements over 1 times your area element. Okay. And then in 3D, you have a similar thing, except now you have a volume element. So anything we do with like centroid or average value, whatever, you'll be using this volume element if it was in 3D. If it was in 2D, you'd be using the area element. Okay, so any questions on those definitions or formulas? Okay, let's do a quick example. So I wrote it on the board so that you can, because I'm scrolling, so it'll still be on there. But if you were to find the centroid of this region, oh, maybe I shouldn't have drawn. Okay, oh well, I already drew. Of the region defined by 0, x, y, z is from 0 to 1, and then x plus y is greater than equal to 1. So we see that the centroid equation, we're going to, right now we're in 3 dimensions. So we're going to have an x bar, y bar, and a z bar. Right here. And then when you find x bars, it's going to be like triple integral. So let's see specifically, like I said, for x bar, it's going to be the triple integral of x over the triple integral of 1. Now, how did I draw this region? Well, we know that x, y, and z are between 0 and 1. And then you have this term, x plus y greater than equal to 1. So I rewrote that so that I knew how to draw it. So if you subtract x on both sides, you get the line. Yes. Because this is in 2D and this is in 3D. Yep. So they're technically all the same, just depending on if you're 2-dimensional or 3D. Yes.
If this example is in 3D, why are you able to look at the bounds only in terms of x, y?
So I just didn't draw it in the xy plane or xy plane, but it is 3-dimensional.
Okay.
I just drew the xy plane so that we can see what this extra condition means. Yeah, so just looking at like the xy plane, for example, so that we can figure out 2 of our 3 bounds. What is y equals negative x plus 1? That looks like this. And if you were to graph greater than equal to, you get this triangle. Notice that I didn't highlight like the whole thing, because remember that x and y are both limited by 0 to 1. So I did not highlight everything above the entire line. You still have to keep in mind your domain. Okay, so now when we're finding the bounds, since we have x and y, why don't we, so what is our equation going to be? We're going to have an x d. Does anyone want to suggest what we should do first? Y, okay, let's do dy. So dy, if we were to start with the y bound, well, right here, we're told that y is less than or equal to 1. no matter what. So that's our greatest value. And then from this equation, we're told that y has to be greater than or equal to this. So just from these two equations, we're already given the minimum and the maximum. So y is going to be from 1 minus x, or negative x plus 1, to 1. And then let's do x. Since we're in the xy plane, it would be logical to do x next. X, there's no other restrictions except that it's from 0 to 1. And the same with z. No other restrictions except 0 to 1. And then you do the same integral. So 0 to 1, y equals 1 minus x to 1. Except now your expression is 1. dy, dx, dz.
What did you? Oh. No.
Yes, sorry, I forgot the dz. Yep. Okay. And so you can do the similar thing with y bar and z bar, which I won't calculate unless people have questions about it. And from there, so I'll leave it to you guys to calculate that, and you'll get that your centroid will be you'll have 3 terms, whatever x bar, y bar, and z bar. Yes?
So in the examples from the videos when the numerators are different for the x and y terms, that's because it's centered.
Yes, because center of mass has an extra density for them. Any other questions on this example before I move on to the mechanics? Yes.
Can we do the y?
Yep. So the y bound would be, so we keep in mind the same formula, except now we're doing the triple integral with y, dx, dy, dz, over triple integral with 1. And so you can, it's actually the same exact thing. Oh, whoops. Same exact thing, because your bounds don't change. Like y is still between this minimum and maximum, x is still between 0, 1, y is still between 0, 1. The only difference is this expression should be a y here. Any other questions on that? Oh, sorry. Okay, let's move on to mechanics. So now we have applications in mechanics. And so we still have the same thing. So we're always going to have like an element, some main thing to calculate, and like other properties. So we see that the mass element distance for n equals 2, so we're in 2D. It would just be the density times dA. And if you wanted to find the mass of some 2D regions, you do the double integral of your mass element. Center of mass, as someone pointed out, is that now you have x. So you would imagine this as like x dm, because no matter what, we want to use whatever elements our like equation is in, and because dm is this density dA, that's why we have an extra component. Yeah.
GM can also be density times dV, right? Like, depending on the dimension.
Density, yes.
Right.
Yep, in 3D. Okay, and then moment of inertia is you have r squared times your mass element. Mass element is density dx dy. So don't forget that there's this extra density. And then next week, we're actually going to learn how to derive why is dm like density dx dy. Okay, and the radius of gyration is this square root of moment of inertia over your mass. So that's in 2D. In 3D, as Javier pointed out, the mass would be rho of dV again. Mass element is rho dV instead of rho dA, because now you're in 3D. Your mass is still rho dV. Center of mass, you have the same like x with rho dV, and so on for the mass. Moment of inertia is going to be the same, except you have a dV here. So you added one dimension, and the radius of gyration is the same. Yeah.
What is radius of gyration?
I don't really know the exact. Oh, Bryce did say something about wait, let me say his announcement. Oh, did you have a question?
I was gonna just like try to answer.
Oh, okay, yeah, go ahead.
I think it's just like it's still moving around the axis, but it's like gyrating in all directions, but while also moving around a central axis. So it's like yeah, like I think the map is the same. It's just like that's the formula.
Yep, that sounds right. So he said, let's see. There are things beyond the basics like radius of gyration may be tested next week, but not this week. So the requiz is just like the base, not the easiest part, but like the basics of this week. So not necessarily easy, but like basics like centroid, center of mass, moment of inertia, PDF, and computing probability.
This week a requiz?
Yes.
So this week, which topics are coming?
Okay, so he said the basics from this week that might be tested possibly are like centroid, centers of mass, moment of inertia, PDFs, computing probability. Yeah, and they're all on the study guide too. So it should be on the study guide. Okay, any questions on these formulas? Yes. Yes, or you could think about it. We'll see a problem later, maybe if you had like a cylinder, like some cylinder, and then you have a axis of rotation. Your R will actually be the distance from any point on our cylinder to your axis. So any point on your shape to the axis you're rotating around. On the exterior. Yeah, so like you can keep like this. Okay, so then we have an important theorem, the parallel axis theorem. So this says that you're given an object with mass m, and it's rotating about some axis with moment of inertia I naught. So the first 2 bullet points you're given. And you want to find the moment of inertia of the same object, but about a new axis. And this new axis is parallel to your old axis. Then the moment of inertia of your object rotating about this new axis should be your old moment of inertia, I naught, plus your mass times the distance squared, meaning the distance between your old axis and the new axis. So that's a nice theorem. Any questions about that?
Oh, wait, what? Oh, yeah.
Okay, so let's do an example. Okay, so suppose the density of a solid object is x plus y, and the object occupies this shape we see with vertices given, but I just drew the picture for you guys. Set up the integral to find the mass of the object. So take 30 seconds to think about how would you set up this integral to find the mass? And mass is, right now we're in mechanics, so all these formulas. For 2D or 3D.
MT squared, the parallel theorem.
Yes, mv squared. Yep. Okay, so let's see. So for the mass of the object, wait, set up the integral to find, sorry, center of mass. Pretend this says center of mass, sorry, center of mass. Okay, so center of mass, we follow the formula, right? Except now we're in 3 dimensions, so it's gonna be a triple integral of whatever variable we have, density dv. So here I have whatever triple integral of, right now, say we want to find the center of mass of y, and then dm, our mass element is density dx dy dt. Okay, so for our numerator, what should our bounds be? And what order should we do our integral in? Any thoughts?
dz, dy, dx.
Yes, okay.
Or either
Yep, dz, dy, dx. Would you like to say your bounds that you got?
my balance for z would be z equals 0,
Hmm?
z equals y,
Mhm.
and then I just do y equals 0, y equals 1, x.
Yes, perfect. So we have our z bounds because imagine drawing a line in the increasing z direction. So you're going upwards. You first go through the flat xy plane. That's z equals 0. You exit at this top like curved plane, which is x equals y. They gave it to us. Once you project it down to the xy plane, now you're left with some like square shape from 0 to 1 and 0 to 1, which is why our bounds for x and y are 0 to 1, 0 to 1. Any questions on how we got those bounds? Okay, so when we put it in, so we have our bounds x equals 0 to 1, y equals 0 to 1, z equals 0 to y. Remember, we're doing y times rho. What is our density? X plus y. So we have x plus y, and then dz, dy, dx. So this is our numerator right now. Would anyone like me to do this integration? Yes, okay. So let's simplify this. This is xy plus y squared. Okay. So we first do the y or z integration. So we get xy plus y squared. Everything here is constant because there's no z terms. So it's just like a constant times z, dy dx. And your z bounds are going from 0 to y. Okay. So let's simplify our expression. So we're going to plug in y anywhere we see z. And so this gives us xy plus y squared y minus, well, when you plug in 0 for z, this term just cancels out, dy dx. Okay, and what does this simplify to? This is xy squared plus y cubed. Now we take the integral with respect to y. So here, this term, the integral with respect to y is xy cubed over 3 plus integral of y cubed is y to the 4th over 4. And you're integrating, plugging in the bound 0 to 1. So wherever you see a y, you plug in 1. So that gives you x over 3 plus a 4th. And then when you plug in 0, it's just all zeros, dx. And so this gives us x squared over 6 plus 1/4 x from 0 to 1, or 1/6 plus 1/4. And that simplifies to 5/12. Any questions on that integration? Okay, and then for the denominator, so we take the same exact bounds, except now our expression is just the density itself. So if we take the same exact bounds, x from 0 to 1, y from 0 to 1, v from 0 to y, we just do x plus y, which is our density, dz, dy, dx. Okay, so your centroid will be the numerator divided by this denominator, which I won't calculate. But you will get that the y centroid, center of mass, right, not centroid, is 5/7. Any questions on this example? Yes.
So you would just like do the same thing for x.
Yes. Yep. And so you'll get like an x bar and a z bar, and you just write it as x bar, y bar, z bar.
Video, like one of them was like symmetrical, so they were saying.
Let me see. That may have been for if it's a sphere, perhaps. I don't think they would, not sure if they would be symmetrical here because you have like different expressions inside.
uniform density. So it's just like because it was uniform density, we knew it could be symmetrical.
Oh, if the density is 1?
Yeah.
Okay, yeah, that makes sense. If the density, I guess, yeah, if the density is 1, like, I guess, and you had like a sphere, for example, like you can imagine what's the center point, like the origin. So I guess then it would be symmetrical there. And yes. Why? Okay. So let's do another example. We do. Okay. Let's do this example. Okay, so consider the rotation of a two-dimensional object about the z-axis. And so the object is bounded by the lines y equals x equals L, and y equals 0, assuming L is greater than 0. So this is our 2D shape right now. For our mass of the object, we're going to say that it is mass of our object is double integral dm, but specifically dm is density dA. So when we do our mass, they gave us our density is this alpha thing. So alpha, and then we're gonna have our, well, that's our density, and we just have dy dx. For our bounds, imagine drawing a line in the increasing y direction. That gives you y equals 0 to x. Out of all those possible lines, the smallest x value is 0, largest x value is L, right? 0 here and L here. And so you can calculate this and you would get alpha L squared over 2. Yes.
I'm confused why this object has mass. Is it two-dimensional?
But you're rotating it. So you're kind of, yeah, so it's not just like flat here. You're kind of rotating it and seeing what the mass of this like rotational object is now. Okay, so then what is the moment of inertia? So moment of inertia, we should first find di. Di is basically like this part without the integration. So di is going to be r squared dm. So dm is rho dA. Now what is r? So r is the distance from some point on our triangle, right? Imagine you're rotating this triangle, some point on this triangle and your z-axis. So if you have our triangle in the xy plane, so our triangle looks like this thing, and we're like rotating it about the z-axis. Well, you can imagine that there's some x component here. So, okay, like this outer part is our point on like the shape if we were to rotate it. And so there's some x component here, there's some y component here, and we want to find what is this purple distance. That purple distance, well, if we use Pythagorean theorem, because this is a right triangle, that would give us x squared plus y squared equals r squared, if we're saying that distance is r. And so we use exactly that for r squared. So when we plug it in, we have x squared plus y squared. Our density is this alpha thing, and then dx dy.
Wait, what do you get the r squared as being x squared plus y squared?
So r squared, we want to find what is the distance between some point on our like shape and the z-axis. And so remember this 2D, this is a 2D thing in the xy plane. So when we rotate it about the z-axis, it's all staying like flat, I guess. And so any point from, if you were to imagine, okay, wait, I'll just draw.
Oh, I see that there's rectangle between x and y.
Yes.
We can say that.
Yep.
Like if it would be rotating about the y-axis, it would be like x squared plus c squared. Right?
Yes.
It depends on the axis.
Yes, definitely depends on the axis, whatever axis you're rotating about. Yep. Okay. So that's our di. Okay, and if we were to find I, you just take the double integral of what we just found. And for our region, this is a 2D region, which is our triangle. So our triangle went from y equals 0 to x, right? If we were to draw, and then x going from 0 to L. So we have the same bounds for our double integral. We're just changing this expression that we're integrating with respect to, and you get this answer. Okay, then the part D says, if the center of mass of the object is this thing, compute the, sorry, that's not the question I want to ask. The question I want to ask is, if we found that the moment of inertia is this, and we wanted to write the moment of inertia as some constant or question mark times m, then how would you write it, is the question. And so what you want to do is we take our moment of inertia that we found, question mark m, we plug in what was that moment of inertia, which was 1/3 alpha L to the 4th. In the first part, we found what m was, I believe, which was alpha L squared over 2. So we plug that in, and then we solve for the question mark. So the question mark is going to be 1/3 alpha L to the 4th divided by this alpha L squared over 2. The alphas would cancel out, and L squared would cancel out, and the 2 would go up. So you have 2/3 L squared. So if it asks you to write the moment of inertia as something times m, well, that something is 2/3 L squared. Any questions on that? Okay, and then radius of gyration is the same. You plug in, so you just follow the formula, plug in what we found for I and m, and simplify. Okay, let's move on to probability. So probability, here we have the same idea. So this is our n-dimensional formula. In 2-dimensional, usually probability is only 2-dimensional, like x's and y's. So our probability element, notice that there's a density here again, but this density is not the same as this density. This is the density of an element. This is your probability density. So they're not necessarily the same. If you wanted to find the probability of some number, here we have the formula. Expectation is x times your element. Our element is density dA. And then our variance is this formula. And standard deviation is always square root of variance. Right? Any questions about the formulas? Yeah.
Do those bars mean like magnitude?
Yes, magnitude or length. Okay, so let's do an example. All right. So we have this. Say D is this region, and our density is C times this. So what value of C makes this a probability density? So think about it for 30 seconds while I write our D. Actually, I'm going to draw a region first. So they tell us that our region is x from 0 to 3. So I'm going to draw, no matter what, x is going to be from 0 to 3. So this region. But then they limit us to saying that y is between 0 and 1. Y has to be between 0 and 1. So our region is this rectangle. Okay. And our density is does anyone have suggestions for what I should do for part A? How do I find C? Yes.
You could integrate that and then make sure and set that equal to 1.
Yep, exactly. So we integrate it. And this is a 2D integration, which we learned last week. So if we wanted to do dy dx, draw lines in increasing y direction, y goes from 0 to 1, x goes from 0 to 3, so it's a rectangular region, and we set that equal to 1. So this integration, if you solve it, you'll get 11c. So you have 1 equals 11c, and we're solving for c, right? So c equals 1 over 11.
It's a PDF has to equal 1, right?
Yes, probability PDF always equals 1. And this is a very common question where they ask you like, what value of c makes it a probability density? You take the integral of your density, set it equal to 1. Any questions on part A? Okay, part B says, what is the probability that x is less than or equal to y? Okay, so what does it mean for x to be less than or equal to y? It means that if we drew this line, this is our y equals x line. If y is greater than or equal to y, should I shade the top half or the bottom half? Shout it out. You want? Okay. So then if we wanted to find the integral, so remember probability is always, we're going to do some integral of our density. So if we do the integral of our density, dx dy, and we want to find the area of this shaded part, if we did like dx dy, yeah, x dy, drawing a line in the increasing x direction, we hit x equals 0 first, and then we hit this line, x equals y. Out of all possible lines, the smallest value is 0 for y. Largest value is 1 for y. So let me fill this in. We have x from 0 to y and y from 0 to 1 of our density function. And make sure you plug in your c that we just found, which is 1 over 11. Okay, and you can solve that and get 7 over 132. Any questions on that part? So if it asks you to find the probability of, they flipped it, y less than or equal to x, that would be this half shaded. And you can find the area of this part. Okay, then part C says, what is the probability that x less than y? Does anyone have a suggestion for what we should do for that? Notice that the difference is we don't have the equal sign anymore. Does anyone, yeah?
Would it not be just the same thing because like the probability that you land on the exact point is 0?
Yes, exactly. So the probability that x is less than y equals the probability that it equals y minus the probability that it's equal to y like this. So less than or equal to y minus equal to gives you less than. But probability that x equals y, that's the probability that you land on this line. The probability of integrating over a line segment, well, there's no area under that, it's 0. So this term is 0. And so you're just left with what we found in part B, this, which is 7 over 132. So you get the same answer. Any questions on that? Yes.
So does that mean if we were doing this, a similar question in 3D, we would be able to just count that as 0?
In 3D, you would be finding, I guess there would be a plane.
Yeah, so the plane has area unlike a line segment, so we can't just discount it.
Oh, wait, sorry, what? I think you wouldn't be able to just say it's the same because then it's like a plane in 3D, or actually it might be a plane, but it has no volume because it's flat. So it might still be 0. Yeah. Yeah, because if you imagine like a cube and you're like slashing it in half, I guess, for like one of the halves, that line is 0. So yeah, I think it's the same concept. Okay. Then part D just says expectation. So I'll just like quickly go over the idea. Expectation, we follow the formula x rho dA. And we're using our bounds of the whole rectangular region. The whole rectangular region, we said it's from y from 0 to 1, x from 0 to 3. And you put in the x, which is x, our density, which was 1 over 11 x squared plus 2y squared, and then dy dx. And if 1 over 11 x squared plus 2, so our density was c x squared plus 2y squared, and the c we found was 1 over 11. Yep, so we can put c is 1 over 11. Okay. And for the expectation of y, same thing, except in our expression, we want this to be y instead. And you'll get 6 over 11. And for variance, following the formula, I believe Bryce also does an example in his videos of these in case you want to get another example. But now we're going to have x minus that expectation we found squared plus y minus that expectation squared times your density, which is in purple now. Okay. Any questions on that? Okay, let's do another example. Oh, yeah.
So the random variables are like capital X, Y, right? And then you're plugging in the source.
No, this is still like a variable x here.
So like, is that X the same as the X that's in the density?
Yeah. Yep. So like think of all these now as variables and you integrate normally. So yeah, so that's why this would be slightly hard to do on a quiz because you have multiple things. But yeah, this like it might say like set up the integral but don't solve. So that yeah. Okay. Any other questions on this problem? Okay, let's do this example and I'll give you a minute to think about it, but let me read it. So it says the probability density for the position of a particle in a two-dimensional box is proportional to x squared y, where xy is the position coordinate of our particle. And we're given some domain. Find the exact expression for the PDF. So just to get you started, what they're saying is that our density is x squared y times some constant, right? We don't know what constant it is because that's what we're trying to find. It's basically saying we're given like that it's c times something. We want to find c so that we make sure it's a PDF. Like we make sure that integrating it actually gives us 1. So it's x times x squared y on our domain and 0 everywhere else besides our domain. Okay. So think about the integral we want to compute. Okay, does anyone want to tell me the bounds I should use to find our integral? Yeah. Yes, exactly. So we have 0 to 1, 0 to 1, 0 to 1 of our density, which right now is some constant we don't know. And x squared y. Doesn't matter what order you do it, I guess. I just did dx dy. Okay, and we want to set that equal to 1. Once you set that equal to 1, why don't we do this real quick? So this gives you kyx cubed over 3 from 0 to 1. Y. Or plugging in 1 for x gives you ky over 3 dy. Or ky squared over 6 from 0 to 1. Or k times 6. So 1 equals k over 6, which means that k equals 6. Any questions on that part? Okay, so now we have that our probability density is 6x squared y if we're in our region and 0 otherwise. Okay, then part B says suppose the box is split into 2 regions in the line y equals x. What is the probability that the particle will be found in the upper region? Okay, so that box, so we have a box in the x going from 0 to 1 and y going from 0 to 1. So right now our region is a box, exactly. We split it into 2 halves, which is the line y equals x. So finding the probability that the particle will be found in the upper region, that is this half, and that's exactly, is that probability of x greater than, oh, is that probability of x greater than y or y greater than x? 1 or 2? 2, yes. So probability of y greater than x. And so that's pretty almost similar to the example we had here. But we have x going from 0 to 1. If we draw a line this way, we go from 0 to 1. And then y is from 0 to 1. Our density in this specific region, we said is 6x squared y, dx dy, and you can calculate it's 2/5. If they said, what's the probability that you find it in the lower region? Well, that's the probability that x is greater than y. So now you have the same thing, except you want this green region. The green region for that, if we wanted to do dx dy again, that will be x, yes, question?
First one, your bounds to be different. Then you actually find this-
Oh, sorry, this is y. Yep, thank you. Dx dy. Okay, then for the green one, if we wanted to do dx, so x enters at the x equals y line. It exits at x equals 1. Y, out of all these possible lines we can draw, the smallest y value is 0 and the largest is 1. So we have that integral of the same density, dx dy. And that will give you 3/5. Any questions on how I did that? Okay, then part C says, now suppose the box is split into 4 equal quadrants. Without computing any integrals, which quadrant is the particle most likely to be found? So without computing any integrals, does anyone want to just guess? What is the region where the particle might be most likely to be found? Okay, who thinks, oh, okay.
I was gonna say, I think it's most likely to be found when x is greater than y, because because what's it called? The x squared y, like as x gets larger, the probability increases much more than when y gets larger. So like if it, like let's say x is at its like large, like x and y are equal, like the probability like is, it's like x squared takes more of the like control of that.
Yes, so good observation. So the first thing you want us to notice is that our density is x squared y. So if our x is greater, then yes, that increases our density. So we're gonna want an x as a greater value. So it's probably gonna be b or c. Then we want to see, well, y value is greater up here. Y value is less here. So B is going to be the region where we're most likely to find the particle, because you have a great x value and a large y value. The next largest, so our order right now is B is the highest. Next largest is, now you have to use our observation of x squared y. Is it going to be A or C? That's our choices. Well, A has a greater y value, sure, but X has a greater impact. So we want C is going to be our next highest, because it has a greater X value, which has a better impact on the density. Then the next thing will be A, and the last is B, because that has the smallest X value and the smallest Y value. Okay. Sorry. Yes, question?
Is it possible that A would have a greater probability density because it's less than 1 and we're squaring it?
Oh, sorry, this is one. This is
Yeah. So like if we have x squared y
Mhm.
and you have like y is greater than x because x is getting squared, and when you square a number less than 1, it gets smaller. So wouldn't having a higher x make the probability lower?
But we're not squaring a negative number. We're squaring a positive. Oh, less than one. Wait. Region. Wait. Now that I think about it, because if here you have like a half square, down here, fourth square. Because this C would give you a larger denominator, but then Y is also smaller. So like, I guess if you had, comparing over here, if you had a, like, 1/3 squared times something up here, like 5 this, that would give you 5 over 4. Over here, if you had an X, which is larger, big square times this Y, that would give you 25 over 18. So this is larger than this. Yeah, I put the X and Y value choices. So C still gives you a larger value because the denominator might be bigger, but your numerator is smaller. So if you have a smaller denominator over, even though the denominator is larger, yeah, really work out like this. Okay, sorry. Any other questions on that example? So I wrote it in my notes here. Okay, if not, does anyone have any other questions? Yeah. Marginal probability. Let me recall. I don't recall what marginal. Wait, let me